Okay, so time to get started. Let's see, last time we were just kind of starting to play around with ideas relating to single variable integrals and trying to come up with something that might be kind of analogous. Maybe in a multivariable context, I emphasized we're playing around with ideas here. And for whatever it's worth, the idea that we're going to come up with here first is going to have some value, but it's not actually going to be ultimately our right point of view. So file this under a first hack at it, but not ultimately the right point of view. Okay, so here we go. We're going to consider what seems like a reasonable question. In single variable calculus, we looked at graphs. And in that context, the graph of a single variable function gave us a curve under which we tried to compute the area. Here, a graph of a function of two variables gives us a surface under which we might reasonably want to compute the volume. Right? So how are we going to compute the volume under the graph? Is our again, seems like a reasonable first step into this region. Okay, so how are we going to do this? And the big idea is to view this volume. I like to think of it as like a big loaf of bread, and I'm going to slice it into little slices. I'm going to try to compute the volume of each slice, and then and we'll just add them up. Because after all, one thing we know about a loaf of bread is that the volume of the entire loaf is the sum of the volumes of the slices. Right? The whole is the sum of the parts. Nice feature about volume. The whole is the sum of the parts. Okay. All right, so when we were doing single variable volumes of rotation, we were lucky that this volume was just a matter of multiplying the area of a disk. That was easy. Whoops. Oh, I'm sorry, that was my bad little connection here. We were going to multiply the area of a disk times the thickness, and the area of a disk is easy. This is not a disk. And so there is a temptation to say, well, we're out of luck, and nothing we can do about it. But there is. It may not be, this volume, this area might not be a disk or a rectangle or a square or a rhombus or something, but this cross-sectional area is something we do know how to compute the area of. It's the area under a curve. Specifically, that curve is actually kind of a graph. Now, it doesn't feel like it because there's a function of two variables there. The graph of a function of two variables is a surface. That's not a surface. But notice, in order to even be able to talk about this area, I've got to say which area I'm talking about, cross-section for what value of y. I have to pick and fix a value of y in order to even be able to define the area I'm interested in the first place. And if y is fixed, then notice now we don't really have a function of two variables anymore. We have a function of, in effect, only one variable. The variable is x, and based on that x as an input, I get a z as an output, and height is a function of x, and that's a graph. So, actually a pretty familiar situation, and you want to compute this area, fine, no problem. Area is an integral. And now, to be fair, we've got to be careful about this. This is an integral as we move in the x direction, right? It's an integral dx, because that's the variable. How are we doing so far? Is everybody with me so far? We're going to put it all together in just a moment here. Okay. So, looking back again at the start, the first argument I made was that, I'm going to integrate as I go in the y direction. Area times dy will give me volume. So I have a dy integral, the integrand of which is cross-sectional area, which itself is a dx integral. And altogether then, these colors are getting out of hand here. Let me get rid of all of that. Altogether, we're taking a dy integral of cross-sectional area. Cross-sectional area is the dx integral. And grand total, I get an integral of an integral. There's an integral with an integral inside of it. Right? This is what we call an iterated integral. The term's a little unfortunate. To me, the term iteration suggests that you're repeating a exact process multiple times. That is not what we're doing here. I'm just going to put a frowny face on the iterated there. It's fine. This is the common term. This is what you're going to hear. I'll probably mostly stick to this terminology. But I think it's important to recognize that while there are two integrals, yes, it is an integral of an integral. They're pretty morally different integrals. One's a dx integral, one's a dy integral. We're not repeating the same thing twice. So the terminology is unfortunate. Okay. All right. So, question.
Can we flip the order?
Yeah, that's a great question. I'm going to get to that. The short answer, yes, and makes a nice exercise. But I do want to finish fleshing out this, and then I'll come back and say a couple words about that. Yeah. Okay. So, real quick, how are we going to compute this? We're going to compute the inside integral. Once I see what this gives me, that'll tell me what my integrand is for my outside integral. I will then compute that integral, and then we'll be done. We will have successfully computed the volume. Okay. All right. Here's the weird question. Looking at this inside integral, I see two variables. We haven't really done that before, right? Thinking back to single variable calculus, you never had two variables in your integrand. So how do you deal with that? What do you do with the y? What's the story there? Remember, actually a pretty simple answer here. This inside integral represents this area. This area only makes sense in the first place if you say what value of y you're talking about. That is, y has to be viewed as a constant. So it is actually an illusion that it appears that there are two variables in here. No, there's not. In this dx integral, y literally is a constant. So of course we treat it as a constant. This is in fact just a function of one variable. The variable is x. It's an integral dx. Straight up single variable calculus. Okay. Here's another way to think about this, and I think this is a nice little memory trick. Whichever variable is on the outside, that's the one that's to be treated as a constant for the inside integral. Okay. Now that leads me to another little bit of terminology I want to talk about, and that is how do I distinguish these two integrals from each other? We've got that integral, and then we've got this integral. There is a temptation to call one of them first and one of them second. And I claim that's ambiguous because, as we discussed, as we developed this integral, I wrote down the dy integral first. The dy integral is the one that says that the volume of the whole loaf is the sum of the volumes of the slices. That was a dy integral, and it's on the previous page. It came before. And then only second did we make an argument about what the dx integral is. That's our cross-sectional area. That came second. But as we compute, we have to compute the inside integral first. I can't start by computing my dy integral. I don't even know its integrand yet. The integrand is the dx integral. I have to compute the dx integral first, so I know what the integrand is for the dy integral. So computationally, the inside integral could be viewed as being first. So this whole idea that we're going to distinguish these integrals by one's first and one's second is a bad plan. And I very strongly discourage using this terminology because I claim it doesn't mean anything clearly unless you elaborate. You could say, the first slice, the very first slicing that we do is with the dy. Sure. Right? But you do have to clarify and say something like the first slices. Or, by contrast, for the dx integral, you could say, I suppose you could say the first computed integral. Something like that. But all of this is completely unnecessary because much easier, much clearer, dx is on the inside. There's no ambiguity as to what that means. And dy is on the outside. Again, unambiguous. Okay, so please do be careful about the terminology. Let's see an example. We're going to compute the volume under the graph of that function, which is going to be a paraboloid. And if you think through, the part of the paraboloid that we're interested in there, it would look something vaguely like that. Specifically, we want to know the volume under that surface sitting over this rectangle that I have drawn here. Now let me take a pause on the question to talk about notation. What do I mean by this weirdo notation with the cross there? This is just a convenient notation for representing a rectangle. It's very handy. The first interval here is just telling me the interval on the x-axis, sort of, if you will, the x shadow of the rectangle in question. And then the second interval is the y shadow. And I think you can see that by describing the range of values for x and the range of values for y, it follows what the rectangle is that we're talking about. So very handy notation. Heads up for that. I'll be using that notation significantly, I'm sure. Okay. Right, so compute the volume, and we argued that above. The volume is this iterated integral. Integral of an integral. And now we plug and chug. There's just a couple of things to be aware of as you plug and chug. First, an easy bit. The x antiderivative of x squared gives you 1/3 x cubed. Single variable calculus, I'm sure you'll all remember. Here's the tricky bit. X still being the variable. What am I going to do about y squared? What's the antiderivative of y squared? Now, a lot of students play this a little too sort of carelessly, a little too quickly, and 1/3 y cubed. You can see the temptation to write 1/3 y cubed, but it's not. And very importantly, and this is an idea we mentioned just a few minutes ago, the outside variable is to be treated as a constant for the purposes of the inside integral. So y is a constant. That means y squared is a constant. And when you take an antiderivative of a constant, you get constant times variable. So the antiderivative of y squared is just x times y squared. How are we doing on that? Everybody okay? Real tricky little bit. You'd be surprised how easy it is to mess that up. So one of your jobs as you go through and compute iterated integrals is to always be paying very careful attention to, wait a minute, as I go through here, which variable is playing what role inside of whichever integral I happen to be looking at the time, right? And for this inside integral, x is the variable, y is a constant. I mean literally, right? Y is literally a constant as I compute this inside x integral. Right? Nothing make-believe about it. So treat it as such in the algebra. Okay. All right, the last little observation I'll make, and this is more so advice than it is a technical point. When you are doing the x integral, the bounds are 0 to 1, so you write down your 0 and your 1. I find a nice little hack is to indicate specifically x equals. Because as you're plugging in these numbers, so for example, as you're taking 1 and plugging it in for the variable, in this case x is the variable, but as you're plugging it in, it's easy to kind of inadvertently, accidentally, oops, and plug it in for y also, which of course you shouldn't do. Y is a constant. It's not ranging from 0 to 1. X is ranging from 0 to 1. Y is a constant. It just stays there. So I find it helpful. Again, it just prevents me from doing something goofy to actually write x equals 1 and x equals 0. It's not required. You don't have to. I think it's a good idea, and I strongly encourage you to do it. Yeah, go ahead.
Question: how come you write like a parentheses right there in that line, and when you're evaluating x?
I'm sorry, I don't know. What do you?
You see where you're talking about like we're placing x equals 1 and x equals 0.
Yep.
Well, and by the integral, you have like a
This bracket?
No, not the bracket. The parentheses. How come
This one here?
Yeah. How come you have one?
Oh, that's just a recognition that what I'm evaluating here is this inside integral.
Oh.
I didn't want any of this to kind of inadvertently get involved, and having parentheses there just makes it more clear.
Okay.
It's I guess not really essential, but I think it's helpful. Yeah. Cool. Yes. Yeah. Okay. Right. Good question. Keep in mind in our slicing process, we have x going from 0 to 1 because it says right there x goes from 0 to 1 as is indicated right there. So so take all together, this tells me my range of values for x, which tells me my bounds for my x integral. Is that cool? Yeah. Everybody else, is that all right? Likewise for the y's. Okay. All righty. Okay, everything else is single variable calculus, yada, yada, yada. Make sure you're good at that. I am going to assume that you're strong with single variable integrals and all that business. Yeah. Good. Okay. Okay. Now, somebody asked, can you slice in the other direction? And yes, absolutely. In fact, let's go back to our original picture. Originally, our first cut at this was to slice perpendicular to the y-axis. That gives us what I like to call y slices that look like that. But if you wanted, and I suppose you can do this with bread too, but I think this would be weird, but you could slice perpendicular to the x-axis. You would get slices that look like kind of like this. And you could talk about what's the volume in that slice, which would require understanding this cross-sectional area, which would require understanding that area as an integral in the y direction for which x was constant. And you can see it would be totally analogous to the argument that we've just made here, which is the roles of x and y reversed. And when you do that, what you end up with is that the volume that we previously computed with this iterated integral could instead be computed by that iterated integral. And notice that both the x and y differentials and the x and y bounds just switch like this here. Right? Now, very importantly, the x bounds are still the x bounds. The y bounds are still the y bounds. So if you switch the differentials, you also have to correspondingly switch the bounds, right? Because it is still an integral inside of an integral. So do be careful about that. Does that all make sense? Is that believable? Now that said, you can take this as a given, but I think it's a really fantastic exercise to think through these details. So take what we did here, where we sliced in the y direction, and instead slice in the x direction. Then you would have a cross-section going the other way, compute the area of that cross-section, and then you'll find your dy integral inside of your dx integral, and it would end up being this. Okay, so think it through. Nice little exercise, good practice. Give it a shot. Okay. Real quick warning, this is going to seem like a silly thing to say. I say here this only works if the domain is a rectangle. It's got to be a rectangular domain. The reason this seems silly is because the only question we've entertained so far is the idea of where the domain is a rectangle. So what other case am I referring to? It's going to turn out, we're going to not be able to get to it today, but on Monday, we're going to start talking about what would happen if my domain here, over which I might, for example, want to compute the volume under a graph. What if this wasn't a rectangle? What if this was a different shape? And in those cases where that's not a rectangle, you can still slice in either of two directions. But the bounds don't do this simple thing like we've got here. This lucky break where the bounds just kind of move along with the differentials, that is a peculiarity of rectangles only. So don't get too comfortable with that little fact. Okay. All right, now I have some bad news. Thinking back to single variable calculus. Oh, by the way, let me do this. There we have some more space. Thinking back to single variable calculus. We also, in addition to graph, area under a graph, in single variable calculus, we also computed like the mass of a rod, right? So forget about area. Just on the x-axis, we have an interval from A to B, one-dimensional question, just an interval, mass per unit length given, not a constant. How would you compute the total amount of mass distributed across that entire interval? And typically we think of like a metal rod that has a varying cross-section or something like that. Okay. So what was nice about single variable calculus is that the integral we use to compute area under a graph is exactly the same kind of an integral that we could use to sort of add up those little pieces of mass. The exact same construction works just fine. So, all right, it would seem analogous then that, now that we've got this thing called an iterated integral, and iterated integrals help us compute volumes just fine. If the pattern were to continue, then we should be able to compute the mass distributed across a rectangular box. Given mass per unit area, you would think we could compute that mass with the same tool, just like it worked in single variable calculus. Seems tempting, right? Why not? What goes wrong? Well, it turns out that there's a pretty serious problem here. And here it is. Let me remind you some of the details. As we're going through and computing this inside integral, when you look at f times dx, the whole idea of that is that f represents a height and dx represents a length, and height times length is area. And I know what area is. I can see area, I can relate to area, I understand area, I know how area behaves. And very, very importantly, for the purpose of arguing that I can integrate, in other words, that I can write the whole as the sum of the parts, I know area does that. I know area has this feature that when you slice it up into smaller pieces, the whole is the sum of the parts. And my little convenient term for talking about this is that area is an accumulating quantity, or area accumulates. The whole is the sum of the parts is all that means. So again, I know that I can do an integral to compute the sum of these pieces because I know area behaves that way, and I know that area is what we're talking about. Okay, fine. So now let's analogous thing. Let's look at what would happen if I were to write down this iterated integral in an attempt to compute mass. I would find myself then looking at mass per unit area and multiplying that by length. And what do you get when you multiply mass per unit area times length? And I'm going to say I don't really know. That's not really what mass per unit area is for. The big idea of mass per unit area is it tells It says, look, if you come to me with an area, I'll tell you how much mass is in there. That's what mass per unit area is for. I don't know what happens when you multiply mass per unit area times length. Not a thing. And you could say, I suppose you could say, well, it's mass per unit width. Okay, well, what's that? How does that behave? Is that something we understand? No. It's a brand new idea that we've never thought about before, and we can't just go around asserting that you can whole is the sum of the parts, because we don't know it accumulates, because we don't even know what that is. We have no previous familiarity with mass per unit width. Right? So the argument just doesn't, any argument that you might make that would assert that mass is an iterated integral, it has some serious problems with it as an argument. Lots left to be filled in. What is this quantity? How do you know it accumulates? And here's the thing. It can be done. You can do that. It does accumulate, as it turns out. It's really not clear. But even if you argue that it does, then I'm going to have a next question, which is, okay, maybe we're not computing mass. Maybe we're computing population or work or any of a million other things that we've computed with integrals in the past. And are we going to have to go through and figure out what the quantity in question is every single time for every one of those examples? This is a bad strategy. It just doesn't work well. So, roughly speaking, we're kind of dead in the water here. This is not going to be a good strategy for how to compute stuff. Okay. All right. Now, there is a workaround. The workaround, this is a very important thing. We're going to define something called a double integral. This is not a single variable integral of a single variable integral, like iterated integrals are. This is a completely different construction. A double integral is an attempt to let's not get distracted by our first application. Let's think about how to generalize the fundamental idea of what an integral is in the first place. So in order to do that, we need to be extra careful to make sure that we are clear on what an integral is in the first place. And specifically, a single variable integral, it's very important that we be all on the same page here, is a Riemann sum. Area under the curve is a nice little application, I suppose, but it's not that useful, and it's certainly not a good definition. The formula f of b minus f of a is wonderfully powerful theorem, but it's not a definition. Right? As a definition, a single variable integral is a Riemann sum. Now, let me try to persuade you how useful this is. This is a lot of people mistakenly think that this is mathematicians having fun being abstract ivory tower, irrelevant to the real world. That is absolutely not what's going on here. This is really, really important for applications. As follows: let's pretend that we didn't have Riemann sums. No Riemann sums. Now let's suppose we were to define integrals as just being area under the graph like this. And it's very satisfying when you want to, compute. If you're interested in just area under a graph, then great. This, you can draw some pictures and call this the fundamental theorem of calculus and get an answer. And everything seems fine and dandy until you try to apply this to a real-world scenario. And in a real-world scenario, let's suppose you want to compute the amount of mass. Let's suppose you want to compute the amount of mass distributed across an interval. Right? And we know an integral can do this. But how do I make the case that mass distributed across an interval can be computed with an integral? Can I just claim as self-evident that mass distributed one-dimensionally is the area of something that wasn't even given in the statement of the question? No, it's really not clear at all. Mass is mass. area has nothing to do with mass if the mass is distributed one-dimensionally. There is no area to talk about. And yeah, you can make up and talk about the graph or the density function, but then how do you know that that's got anything to do with the original question? It's really not clear. That is not clear at all. So this idea that you can connect applications directly to area is that doesn't work. It doesn't hold any water. As an argument, it doesn't make any sense. Now here's what you can do. I'm going to abandon all of this. What we can do is argue that mass is an accumulating quantity. The whole is the sum of the parts, and I can write down a Riemann sum. Right, the total mass is the sum of a bunch of little pieces of mass, which I can express, like I say, as a Riemann sum, aka an integral. Now, having done that, having argued that the whole is the sum of the parts, chop it up, add it up as Riemann sums describe, then I can subsequently say, hey, and by the way, if you're unhappy with the idea of a Riemann sum, it's very algebraic. I'll grant you that. And if you want to visualize the Riemann sum, then you can try to understand the Riemann sum as an area. Okay, that's fine, but it's optional. It's really not necessary. You don't need to visualize the Riemann sum for the Riemann sum to represent the mass. This is just straight up true, right? And what's definitely the case is that the Riemann sum is not optional. You have to have Riemann sums before you can even talk about how you might interpret that as an area. Okay, so this is why integrals, importantly, have to be viewed as Riemann sums. All right, and then, of course, we have a fundamental theorem of calculus that helps us compute Riemann sums, aka integrals. And notice at this point, area is an afterthought. Area under a curve is it's one application among many. It's not even a particularly important application in the real world. How often, seriously, how often in the real world do you need to know an area? Not that often, right? Most of the time in the real world, you need to compute stuff, physical stuff, mass, work, whatever, population, right? Area is a crutch. So please don't be confused as to what an integral is. Very importantly, integrals are Riemann sums. Okay, now with that in mind, and based on that, let's try to generalize. Instead of looking at an interval and chopping that up into a bunch of little pieces, and then answering the question at hand on each little piece and adding those up, like so, our usual Riemann sum expression. What if instead of this one-dimensional interval, what if I have a two-dimensional rectangle? Come on. Okay, it was a little messy, but anyway, what if I have a two-dimensional rectangle? And the idea of what I'm going to do, I'm just going to rip off the idea we did over here. What we did with this one-dimensional domain is I chopped it into little pieces, and I argued on each little piece there's, I don't know, mass per unit length times length, or area per unit length times length, or work per unit length times length. So stuff per unit size times size is what we write down, because that's how the little questions work on the little pieces that we then add up in an integral. So I'm going to just do the same thing over here, two-dimensionally. I'm going to basically think about how can I chop that up, and then when I do, how do I add up all the little corresponding pieces? Well, the chopping up is pretty straightforward. The chopping up on the left over here, we just literally chopped it up. And so I'm going to do the same thing over here. I'm just going to slice up the domain like that, except now I also have to slice in the other direction too. Okay, now I've chopped it up into little pieces. Notice as I chop up my rectangle, I am also inadvertently chopping up the x-axis exact same way we were in single variable calculus, as it turns out. Still an interval from A to B on the x-axis. I'm still chopping that up into n pieces. It's very familiar. I am also, as it turns out, chopping up the interval from C to D on the y-axis. And as I do that, analogous algebra gives me a formula for delta y and a formula for y sub j. So the act of chopping up my rectangle gives me a bunch of details to keep track of. It's just details. Don't get lost in the details. And I'm going to argue that on each little piece here, so let's look at this little piece of area right there. Whatever question I might be interested in that's hard to answer on the whole, presumably is relatively easy to answer on each little piece. So, for example, again, let's imagine that mass is distributed across this rectangle with density varying wildly, right? Well, yeah, okay, sure, but on this little piece, density is approximately constant. Mass per unit area, I can just multiply by the area. Perfect, right? The Legos fit together. Mass per unit area times area. Easy to write down. Or wait a minute, maybe I'm not computing mass. Maybe I'm computing the population of Wyoming. Right? Okay, well then population per unit area times area. Oh, maybe not population. Maybe I'm computing the amount of work that it takes to perform a certain task. Okay, work per unit area times area. Right? There's a million, endless supply of applications where I might, on any given little piece, be easily capable of describing quantity per unit area, and then I would just multiply by area, and then I just add up over all of the pieces. So, how are we going to compute this? This whole separate thing. We'll get to the computation on the next page. But for the moment, just strategically, whatever quantity I have, if it's an accumulating quantity, if the whole truly is the sum of the parts, like mass, the whole is the sum of the parts. Population, if you subdivide Wyoming into a bunch of little pieces, the whole population is very clearly the sums of the individual pieces of population. I mean, any accumulating quantity, this construction right here will allow you to compute that whole as the sum of the parts. And it's a total analogous rip-off of what we did over here in single variable calculus. This is just a natural sort of extension of that. Okay. All right, so this is what we're going to call a double integral. This expression right here, call it a double integral. We're going to use this notation right there. The idea of the notation, by the way, is that this is recognition that what delta x, delta y is doing is really just helping us understand the area of one of the little pieces. So we're going to call that dA. And as you might expect, we're going to use a notation to represent all this summation and limit business. We're going to use two integral symbols like that. Just kind of as a nice little shorthand. Okay. All right, so this is what a double integral is. Now, it remains yet to be determined. How am I going to compute these things, right? Again, I freely admit, yeah, that's going to be a problem. That's something we got to figure out. But this is the two-dimensional analog of a single variable Riemann sum definition of a single variable integral. Okay. Now, the book does some very cool stuff that is not Math219 appropriate. It turns out that this expression right here, which works great for continuous functions, doesn't work so great for discontinuities. It turns out there's a bunch of different ways in which a function can be bad. and inconvenient, and mathematicians like to spend a lot of time thinking about, okay, well, how bad is your function, and how can we make sense out of an integral in such cases? And there is some tremendously interesting math that goes into that. It's all very classical kind of math. It's beautiful stuff, and if you're a math major, take a course in real analysis. Wonderful material. But that's not what Math219 is. The book's discussion of irregular partitions and test points is very important for treating all this carefully and rigorously appropriate to a real analysis course. And it's just a little bit much, I think, for Math219. So you are absolved of any responsibility for irregular partitions and test points. You can take a look if you're curious, but you don't need to read that stuff. Okay. All right. Let's do an example. We already know how to compute the volume under a graph. Right? That volume. We know how to do it. Iterated integrals. Done. Fine. Let's do it a different way, though. Let's use this as our first example of our shiny new tool called double integrals. And I'm going to argue that while you could view this volume as a loaf of bread that you slice into slices of bread, you can also view this as a bunch of French fries that make up a biggie French fry, and the whole volume of French fries is the sum of the volumes of the individual French fries. So, individual French fries are really easy to compute the volumes of. It's just height times the area of the base. So, some function, the function whose graph we're looking at, right? The function that gives us the height, the function that gives us the z, and then we multiply by the area of the base. And so there's this little base down there that has a certain amount of area. That's our dA, as it were. So, like I say, any individual French fry, it's easy. It's just height times the area of the base. And the whole is the sum of the parts. So I can argue that grand total over all of this rectangle, we just add them up like that. And then notice that, in fact, lo and behold, very conveniently, as it turns out, we have exactly a Riemann sum, and thus double integral. How are we doing? Is everybody with me? Okay. Great. Now it remains. We don't know how to compute these things. What good is it to have a tool for answering questions that leads to an expression that we don't know how to compute? So let's talk about how to compute it. It turns out a really clever argument we can make here, and that is to point out that, look, yes, we just got through showing that volume can be computed with a double integral. That's what we just showed. But don't forget, we have previously showed that that same volume can be computed with either of these iterated integrals. And wait a minute, if you can compute the same thing with two different expressions, that means that these two things are equal to each other. And that's really actually the main reason why I like this example, computing volume with a double integral. It's not because volume is something we particularly care about. Again, it's kind of like area under a curve. It didn't really come up that much. Every so often, I suppose, and maybe volume comes up a little more often, but still not really our point. The purpose here is that this computation of volume allows me a conclusion that I can compute any double integral with a corresponding iterated integral. That's the big payoff. So all of this together allows us to draw the following diagram here. This is kind of a summary of everything we've done so far. We started off by computing volume under a graph. We derived this thing called an iterated integral. We plugged and chugged. That was nice and all, except it wasn't good for anything else. We had to recognize you can't just argue that mass is a volume, because it isn't. You can't just compute mass immediately with an iterated integral because the argument doesn't make any sense. The units don't work. We were multiplying mass per unit area times length. It's just, it doesn't work. The argument doesn't hold together. So we just got through computing volume with a double integral and concluding that double integrals can then be turned into iterated integrals. And now we have a way out. Now we have a way to actually solve problems. If you want to compute the answer to one of these applications, write it as a double integral. Then you can say, hey, by the way, guess what? Double integrals can always be computed with iterated integrals. Isn't that nice? And iterated integrals we can punch up with the fundamental theorem of calculus. That's the three-step process. There's a bunch of little details we had to deal with there, but very important sort of details. So remember, the reason we need double integrals is to connect to applications. Iterated integrals can't do it. Right? You just, colors. That doesn't hold water. Iterated integrals we can compute, and that's nice, right? But they don't connect to applications. But then there was this other problem that double integrals that connect to applications, we don't know how to compute. Right? So being able to turn double integrals to iterated integrals connects something that relates to applications with something that we know how to compute. And again, thus the sort of the three-step strategy. So let's see this in action. We're going to now finally answer the question, how do we compute the mass in a rectangular sheet where mass per unit area is given, right? Some rectangular sheet like so. How are we going to compute that mass? Well, step one, let me do the broad strokes first, and I'll come back and do details. Step one, mass is a double integral of density. Come back and do the details momentarily. A double integral is an iterated integral, like on the previous page. And iterated integrals I can compute with the fundamental theorem of calculus. There's our three steps. Just like in the diagram that we just talked about. Yes, question?
Is the purpose of the three steps more so just for understanding?
Yes. Yeah, that's right. Yeah, exactly. So that's a great question, and this is something, I have my little soapbox that I'm constantly on about, hey, this isn't a course about answers, it's a course about ideas, right? Exactly what you said. Yes. If all we cared about was answers, we wouldn't be doing this stuff, right? But it's not what the course is about. This is a course about understanding ideas, just like you said. So, yeah, I want students to realize why do we need to worry about the distinction between double integrals and iterated integrals? Because it's kind of a big deal, right? Because iterated integrals really don't connect to applications. And double integrals, really, we don't know how to compute them. Yeah, absolutely. Yep. Okay. All right, now some details that I skipped over. Let's see how we're doing. Okay, yeah, so real quick, and then we'll call it a day. I say that mass can be computed with a double integral. There's little parts that go into that. First of all, mass is an accumulating quantity. Now, this is a very cautious first step, but the whole is the sum of the parts. That's how mass works. Not everything has this feature of the whole being the sum of the parts. Right? Certainly not. But mass does. Mass is a quantity that behaves. It's an accumulating quantity. The whole is the sum of the parts. Secondly, we understand density in this context as mass per unit area, which means that mass per unit area times area gives me mass. So again, now the Legos fit together here. Mass per unit area is made to be multiplied times areas. And that's all we're doing here. We understand mass as mass per unit area times area. And then we find ourselves looking exactly, literally at the expression that is our Riemann sum, that is our definition of a double integral. So there's kind of, 3 littler steps on the inside here. In practice, though, you're very welcome to, on an exam or on the homework, to just immediately write mass as being a double integral. Now, I do want to emphasize one thing here, though. You cannot skip over the double integral. If you take your application and first thing you write down is an iterated integral, and you just kind of don't bother with that, notice that is indistinguishable from this that we just got through talking about. Doesn't make any sense, right? Now, it's not about the conclusion. Yes, you get the same iterated integral. It's not about the answer. It's about your argument. Does your argument demonstrate that you understand the relevant ideas? Double integrals are a really big deal, right? It's central to what we're doing here, what our computational strategy is. So if you just kind of don't bother writing that down, your work is indistinguishable from that of someone who doesn't understand double integrals in the first place. So remember, you've got to represent your understanding, flatteringly, right? If there's an important idea I need you to understand, show me that you understand it. Give me that double integral. And so on a question like this, you can write that mass is a double integral, which is an iterated integral, and then compute with the fundamental theorem of calculus. And I definitely need to see that. Okay, this is a good place to draw the line. We'll pick up here on Monday. Y'all have a great weekend. See you later.